In this video, I want to talk about eigenvalues and eigenvectors of 2 by 2 matrices. We've already done one example of a 2 by 2 matrix with eigenvalues and eigenvectors. I'm going to specifically focus on just the eigenvalue component in this video. So what we're going to do first, and I want to show you something that happens that's very nice. I'm going to take just an arbitrary 2 by 2 matrix, A, B, C, D. And what I want to do is I want to look at the characteristic polynomial. And what we're going to do then is I'm going to look at A minus lambda I. And that's going to end up being, so we're going to take A, B, C, D. Minus, if I take the 2 by 2 identity here, I'm going to have 1, 0, 0, 1. And if I multiply by lambda, then this is going to be lambda, 0, 0, lambda. And so therefore, if I subtract them, we're going to end up with 1 minus lambda, b minus 0, so that's b, c minus 0, so that's c, and then finally d minus lambda. So if we take the determinant of a minus lambda times I2, what's going to happen is we're going to have, we're going to have a minus lambda times d minus lambda minus bc. And this happens to work out to be AD minus D lambda minus A lambda plus lambda squared minus BC, or you can rearrange that to lambda squared minus the quantity A plus D times lambda plus AD minus BC. The AD minus BC, I hope, jumps right out at you. That's a quantity that we know and love, or know and loathe. You love it, let's be honest here. So AD minus BC is the determinant. It just won't go away. And A plus D is also a quantity that we know. A plus D is nothing more than the trace. This is the trace of A times lambda. All right. So it turns out that the characteristic equation, the characteristic polynomial, I should say, of any arbitrary 2 by 2 matrix has this form. Okay, so lambda squared minus the trace of A times lambda plus the determinant of A. And that's particularly nice. So that tells us, just to revisit our last example, in the last video, in the previous video, we studied 2, 5, 1, negative 2. Here, A has determinant negative 9 and trace 0. So that means that our characteristic polynomial, which we call P of lambda, remember, was lambda squared plus 0 lambda minus 9. And if we were to have A being the 2 by 2 matrix, which is, say, 3, negative 2, 5, negative 3, this would lead us to have a characteristic equation, characteristic polynomials of lambda squared plus 1. And therefore, what are the eigenvalues? The eigenvalues are going to be when lambda squared plus 1 is equal to 0. And therefore, lambda is going to be plus or minus I. Here, I is the complex number, so that when you square it, you get negative 1. So eigenvalues are, in general, going to be complex numbers. What if we were to have A is 2804? Well, if that's the case, then our characteristic polynomial would be lambda squared minus 2 plus 4 is 6 lambda plus 2 times 4 is 8. And so we would end up with, if we wanted to set our characteristic polynomial equal to 0 to find the eigenvalues, so our eigenvalues are going to be lambda equals 2 and 4. Okay, and this is going to be the case for any triangular matrix, including diagonal matrices. This will be important. Okay, so for any triangular matrix, meaning that anything below the main diagonal is 0 or above the main diagonal if that's 0, including if they're both 0, so if it's a diagonal matrix, the eigenvalues are just going to be the values on the main diagonal. All right.